Welcome to Ogo Reviews. In this video, we're going to be looking at how to determine the R or S configuration of a molecule. In order to understand this, we're going to take a look at the structure drawn up here. So if you have any molecule that has 4 groups attached to it, if you have a carbon here that has 4 different groups attached to it, we refer to this carbon as the chiral center. It could be carbon, sometimes sulfur, and even nitrogen. Just that the most common one we're going to encounter is carbons. Now, these 4 groups are arranged in such a way that their mirror image can never be superimposed. So let's see what we mean by that. So if I were to put a mirror right here to reflect the exact image of that, so I'm going to have a reflection of this molecule, as you can see in the model kit. So let's begin off by looking at our chloride will be right here. Our hydrogen will be right there. And of course our OH group, because it's a mirror images, will be the farthest away. So you're going to have that. And then of course you're going to have your CH3 group at the top like that. So now that we have this as a mirror image, you can see in the model kit is that these 2 groups, or these 2 molecules I should say, so let's say molecule A and molecule B, they seem to look alike, right? They are mirror images of each other. These 2 molecules which are mirror images of each other are called enantiomers. So enantiomers are just mirror images of each other. Now, these 2 mirror images, because the groups are different on the same carbon, cannot be superimposed. You can see that in the illustration in the model kit, that when you try to pick this whole entire molecule and kind of sit it on top of this molecule, some parts of it will overlap, others will not, as you can see in the model kit. And that is what we are referring to as the configuration. What it means is that A and B are arranged in space differently. So arrangement in space, which is equivalent or almost the same as what we call stereochemistry, pretty much describes the R and the S. Okay, so these mirror images, one of them could be the R or one of them could be the S. And we're going to learn the rules that govern the assignment of R or X. So this is pretty much what chirality means. Now, if you do have these enantiomers in the same amount, in the same proportion, so if you have 50% of each, of either the R or S, of either the R or the S, we have what we call a racemic mixture. So let's take a minute and look at the following molecules and identify the chiral centers in each one of them. In these examples, we're going to identify the stereocenters in the following compounds. You can pause the video and try it out yourself. So let's begin with number 1. So the first thing you do is that you identify all the carbon centers in this molecule. And you realize that at the points of intersection where you have multiple groups attached, tend to be the stereocenters. Now, you can fill in these hydrogens and you realize that, for instance, in this place, you have 2 hydrogens attached and therefore it is disqualified as a stereocenter. All the groups on that particular carbon must be different. So what it means is that we're going to disqualify this point as a stereocenter. What about here? Yes, we do have groups attached to it. And every time you're considering stereocenters, you have to look at the whole entire group attached to that carbon. This is very, very, very important. So what do I mean by that? So if I'm looking at this carbon right here, then I'm considering this group, that group, this group, and of course there's a hidden hydrogen attached as well. That is how you're able to identify stereocenters. All those 4 groups are different and therefore this will qualify as a stereocenter. Let's go on to this carbon. again, you're going to consider all the groups attached to it. So that is another one is different. That is different. And this whole entire group is different. And then the hydrogen, which is not written, is also different. So that makes that center also stereocentric. Now let's go on to this position right here. You can straight away know that there are two hydrogens attached, and therefore this cannot qualify to be a stereocenter. Now what that means is that we only have two stereocenters in the structure 1. Now there is a formula to calculate how many stereoisomers you can get, which is 2 raised to the power n. So n is the number of stereocenters in the structure. So in this case, you're going to have 2 raised to the power 2 giving us 4 possible stereoisomers from this structure. But because we haven't identified whether this is wedged or this is dashes, we will assume that there's a 50-50% mixture of, or I would say 25% each of the isomers, in order to identify how much isomers you have in the structure. Let's go on to example 2. In example 2, we will see that the wedges and the dashes are shown, which means you can actually assign the configuration of this particular molecule. Now, we're not going to do that for now. The next thing we're going to do is to learn the rules on how to assign them. But how do you identify the stereocenters? This one makes it easy, because as soon as you see the wedges and the dashes, it's a sign that yes, there's a stereocenter here and there is a stereocenter here. If you're in doubt, we can also do the same thing we did before, identify all the 4 groups. So here, that's the methyl group is different. And in a cyclic structure, you go all the way around like that. That is one group. That is different. And then the other group will be going around this way, all the way in, to make sure that that one too is what? Different. So of course that is different. And then there's a hydrogen that is different. So you have 4 different groups attached to this point, making it a chiral center. The same thing applies to that methyl group. So overall, you realize that this has 2 stereocenters and will have 4 stereoisomers. Now let's move on to 3. In 3, the same approach. Because the dashes and the wedges are not identified, we assume this is a racemic mixture of 50-50 or 25%, depending on what stereoisomers you have. Now, the hydroxy group is where you have 4 different groups attached, and then where the bromo group is where you have 4 different groups attached, and that will give us 4 stereoisomers. Going to example 4 is a little bit complicated, but it's the same principle. Whenever you see 2 hydrogens, that is disqualified. So you disqualify here, there, there, there. All the points where you have 2 methyl groups are sort of anything more than methyl, or it has 2 hydrogens, are kind of disqualified. So that takes away a lot of these points on the structure. With that in mind, let's identify which areas that you have multiple groups. Again, it has to be 4 different groups at this level. So this is also disqualified. But then you can see this place has multiple groups attached to it, 4 different groups, that the same here. You can say the same thing here, there, and also here. So all these areas are qualified to be stereocenters. Next, let's look at how to assign the absolute configuration of the following molecules and the rules that govern it. So, looking at the molecules, the first thing that you need to know is that you have to identify the chiral centers. So, let's try and identify the chiral centers in these molecules. For number 1, the chiral center is located right there. For number 2, it is located right here. For number 3, that is located on this carbon. And in 4, you're going to have it located over here and there, and even here. So the good news is that at least you're able to identify the chiral centers. However, there are certain rules that govern the assignment of R or S configuration. The rule is called the Cahn-Ingold-Prelog rules. What does that mean? So the first thing you do is you identify the chiral centers. Then next is you assign priorities based on atomic numbers. So every group on that chiral center will be assigned priority based on their atomic number. What that means is that a carbon will have a less priority to a nitrogen, which will have less priority to an oxygen, and so forth and so on. Because carbon is 6, nitrogen 7, oxygen 8, sulfur 16. So depending on what is attached, their priorities will be assigned as such. And then when you finish, you now will assign them based on, like, rank them 1 to 4. Okay, and then 1 will be the highest, whilst 4 is the lowest. And what you do is that you kind of look at what direction that you're going from 1 to 4 or 1 to 3 or whatever. The direction, if it's clockwise, that is going to be an R configuration. But if it is anti-clockwise, if it's going against the clock direction, that will be the S configuration. In order for this to hold, the lowest priority, which is 4, should always point away from you. So 4 should be pointing away from you. What that means is it should be in a dash configuration. And 1 should be pointing towards you. It should be in a wedge configuration. Otherwise, whatever rotation that you got has to be reversed. What it means is if you had an R, the actual configuration is an S. And if you have an S, the actual configuration is an R. So always remember that rule, that the 4 should point away from you, and the 1, which is the highest priority, should point towards you. All right, so let's begin by looking at these examples. So let's begin with number 1. The first thing is we've already identified the chiral center. The next thing to do is to assign the priorities of the groups attached to the chiral center. So we will see that we have nitrogen here, we have carbon there, and we have another carbon. Now, we can assume that nitrogen will have the highest priority because it's 7 versus 6 and 6. So of course, we're going to assign the highest priority as 1 to this nitrogen. The next one is to pick between this carbon and that carbon. Of course, they're the same. So you move on to the next atom, which is oxygen for this group and another carbon for that group. So that means this is going to have the next priority, which is 2. And then the third priority will be this carbon, which is 3. But what you should remember is that there's a hydrogen which is going away from us, and that is going to be priority number 4. So if you look at this, you can see that if you were to draw the rotation, it's going to be very straightforward. So you're going to be going from 1 to 2 to 3. And by doing that, it means you're going counterclockwise. So the absolute configuration of this is going to be an S. Now, let's move on to the next molecule, which is right here. So here is pretty straightforward. You have chlorine, oxygen, carbon, carbon. Of this, chlorine is of course 17, oxygen is 8, carbon 6, 6. So it makes life pretty easy. So chlorine is going to be the highest priority at this point. So let's go ahead and assign that number 1. Oxygen will be next, so you're going to have number 2. And between these two carbons, they're the same. The next one here has a carbon, so this is going to have the next highest priority. And the 4th lowest priority will be this. So now the question remains, which direction are we going? We're going this way, right? So we realize that the highest priority is facing away from us. So as you can see, we have 2, 3, 4, which is this direction. And the highest priority is actually away from us. So we are doing clockwise at this point, which is an R. But then because the highest priority is facing away from us, we're going to have to reverse that to an S. All right. So every time you have the highest priority away from you, you have to reverse the absolute configuration. Or in other words, if the lowest priority, which is a methyl group, is not the one that is away from you, you have to reverse the priority. Let's move on to question number 3. So the same approach. You're going to have oxygen, highest priority, number 1. We have the next one will be this carbon right here. And this will be the next carbon of priority. And 4 will be this hydrogen. So as you can see, we're going in this direction. And this is counterclockwise. So that is supposed to be an S. But the highest priority group is actually away from us. The reversal of the absolute configuration giving us an R as the assignment. Now let's look at question number 4. In question number 4, this carbon right here bearing the hydroxy group does not have a wedge or dash assigned, and as we already mentioned, it becomes very challenging to assign whether it's an R or an S. Now let's focus on the other 2 chiral centers, specifically this one right here. Let's try and assign the priority around this particular chiral center. So we will begin with the atoms attached. So we have a carbon here, another carbon there, and a carbon here. So because they are all the same, we move on to the next atom. If you did so, over here it could be a carbon or a hydrogen. The same thing applies to this. It could be a hydrogen or a carbon. However, when you move up here, it could be a carbon or another carbon. So this one is going to have a higher priority compared to the ones at the bottom. The same way, something that you need to know is that tertiary carbons will have higher priority over secondary carbons, which will have higher priority over a primary carbon. So this is something you can add to your knowledge. So what it means is that now our carbon that is directly attached here is going to have assignment 1. And this right here is going to have 2 because remember, on this one has a hydroxy group which will be higher than anything on this side. So the third will be obviously this carbon on your right. The 4th will be the hydrogen that is facing towards us. So if you watch closely, you realize the order of movement is counterclockwise, making this from here is going to be an S configuration. However, the hydrogen is facing towards us, so that will switch to an R configuration. The same thing can be done for the chiral center right here. Please do that and put the answer in the comment section.